Na, 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 na. Na, 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 na. Ti-da-da-da. Okay, I'm waiting for the YouTube stream to begin, and I'll sing you a song. Very nice, very nice. We got it. Okay, so no time for songs. I was gonna sing the Mariana song. It keeps playing in my mind, in my head. All right, so I just ate something, and as I was preparing the food, I was listening to a podcast, a YouTube video by Science Click, one of the more respectable scientific YouTube channels, about the fabric of the fabric of reality and stuff, black holes, and I was thinking, so how does a black hole forms? And I've been thinking about this for many years, obviously. And finally I got it. I finally know how to create a black hole, a simple black hole in my mind from first principles. Hello, hello Judas.
Hello.
Hey. So I finally figured out how to form a black hole in a thought experiment from first principles. Would you like to hear it?
Uh, yeah,
Hmm.
but first define what you mean. Like,
So a black hole. Have you ever heard the term black hole?
yeah.
Tell me what you know, because I don't know what you know. So tell me what you know, and I'll tell you what I know, and then we'll discuss how we can create one in a thought experiment from first principles.
Oh, my understanding is that it's supposed to be infinitely dense. Um,
Why do you need it to be? Wait, do you need? Yeah, yeah, yeah. That's a misconception. That is a
uh,
famous misconception. Yes, yes. But do you need it to be infinitely dense? I mean,
that was just my understanding that
okay,
it's
okay,
going to expand infinitely. Yeah.
okay. So
Some people have said that like it's going to concern dimensionality, like it's a two dimension in the three dimensional world. I don't know.
that
You probably know more than me. I don't know.
I don't want to say that I know more than you. All I can say is what you said up until now doesn't make sense to me. I cannot introduce any of what you said into a thought experiment, because in a
Mm.
thought experiment, I really cannot imagine infinite density. I don't know how to imagine it, so I have to strike it off the protocol of a thought experiment. I just don't know.
Uh,
I just don't know. I don't know how to
I guess
imagine. Go ahead.
I guess you can, if you want to frame it into a thought experiment, you can say something to the effect of, uh, like something what you say is cascading or going down a rabbit hole, and it's going on ad infinitum, or something like that.
Yeah, that's a problem. That's a problem. That is a problem. I a black hole. We know from astronomy. We have witnessed black holes. We know they exist. So something that has to do with infinity should take infinite time. It should. A black hole. We know that black holes. We know basically that they form. We know under what conditions they form. We know enough to say that there doesn't seem to be. It doesn't seem to take an infinite time to create a black hole. And if the definition involves infinity, then I don't know how it can form in front of our eyes. So I have to
Uh,
go ahead.
well, there's like two types of infinity: absolute and potential. It seems like, do you know these?
No, but
Potential is
it's
infinity.
the
I
question
don't
is
think about them.
no. I look. I'm looking for a simple thought experiment that we can create a black hole in a thought experiment from first principles. and confirm it to the utmost of our abilities, our imagination, confirm that we have a black hole. And if we can do that, then that is a theory, because right now there is no theory of exactly how a black hole forms. There is no, I never heard of a thought experiment in which someone formed a black hole in a thought experiment from first principles.
Mm.
I mean, you could say maybe a little bit, but so let me try and introduce you to my thought experiment, and you tell me how you feel about it.
Uh-huh.
So let me add a blackboard or a whiteboard. Tell me if you see the whiteboard. It's loading.
Have to authorize.
Tell me if
Yeah,
you
I
see
see.
it.
Yeah, I see it. Yeah.
That's good. Hello, ex Caracalla. How are you?
Okay.
Okay. So let's create.
Well,
Yeah. So let's create a black hole from first principles. So we're actually going to take a neutron to create this black hole. And why do we want to take a neutron? Let's start from what everybody knows. So everybody knows basically how black holes form. So you start with a star that is like much heavier than our sun, and at the end of its life, right, throughout its life, it's losing mass. The sun right now is losing mass. It doesn't just shine, but also there is a solar wind coming out of our sun. Excarakara, you're making just a little bit of noise. Maybe you want to mute your mic when you're not talking. So, so there's always solar radiation coming out of the sun, and there's always star. It's called solar wind, not radiate. It's called wind, and it's actual matter. I mean, there's actual protons and neutrons and actual stuff coming out of the sun. So the sun loses mass, and every star during its lifetime is losing mass. And oh, that's actually not critical. That's not critical. What is critical? Sorry, ignore. We don't need that. That information actually we don't need. How do you undo? Oh, there is undo. We actually don't need that. So let me undo. We just need the star. Let's start from a star. And the star in its lifetime is the way it produces heat. So the star balances. The star is very heavy, so it wants to collapse. Naturally, a star wants to collapse in on itself because it's so massive. Just like the Earth also wants to collapse, but the Earth is held up by itself, by the rocks. So the Earth is balanced. So everything in the universe that has mass, it has to balance the it's wanting to collapse in on itself because of gravity and some internal pressure that it must create in order to balance this collapse. So the sun, for example, it creates heat, and this heat holds up the sun itself from collapsing. So the heat creates pressure. The pressure is actually goes in two ways. I'm going to magnify it. I don't want to get. Anyway, there is a balance. Okay, and at the center. Okay, let's go to the center of the sun or any star. So at the center of a of the star or any sun, we can imagine that there is, right, all over the sun there's matter, there's molecules, and we can imagine a molecule at the center of the sun. And this molecule at the center of the sun if we think about it, so right, the the sun, if we're here, there's no pressure. We don't feel any pressure from the sun. We just feel the heat. Over here, there's a little bit of pressure, and like we can look at the sun like an ocean of water. Imagine the sun is a liquid. So the deeper we dive into this pool, the greater the pressure that we feel. So if we can imagine an atom, a molecule at the center of the sun, then we know that it experiences the maximum pressure. So the least pressure is near the surface of the sun, and as you go deeper, you get to higher and higher pressure. This is akin to planet Earth, that at the surface of the planet you can dig, it's easy, but as you dig further and further, the pressure rises. At this very center of the Earth, the pressure must be the highest. Just like if you dive in the ocean or in a pool, the the further down you dive, the greater the pressure. Do you so far agree? Wait, Judas, do you? Are
Yeah,
you?
yeah. I had to try to find the unmute.
Oh
Yeah,
yeah,
yeah. I'm following. So,
that's good.
yeah, I like the example with the if you jump into a pool, like when
Yes,
you go to the bottom, like it's very very dense. It's very you're gonna like explode basically. That's
yes.
what happens with people as well. They like explode. But
They
yeah, so I
yes,
think if I had to predict what you're going to say, towards the center, like it experiences the maximum pressure, and
exactly.
over time, since it's too big, it's gonna converge in on itself.
No, no,
Like,
no,
could I
no.
just?
I'm
I
not.
don't know.
I'm not going to discuss the. I'm not going to go into too much detail about how. You'll see. You'll follow. If you have questions, you'll ask, and everything will be very clear. All I need
Yeah.
right now is to say that at the very center of the star, we have some molecule or some atom that is experiencing the maximum pressure. That's all we need. Now let's look at this atom. So this atom has a nucleus, like a proton and a neutron, and an electron in the shell, right?
Yeah.
Right, everybody knows that, right? We have an atom. An atom has some nucleus with some protons and neutrons and some electrons in the outer shells, whatever, in the shells. Okay. So far, right? We I promised first principles. From first principles, that means what everybody knows. I'm using known, absolutely uncontested, not absolutely because some people don't believe it, but fine. I mean, this is what we've been taught since kindergarten and before. Let's continue.
Uh-huh.
So this is now an atom. Let's dive one. Let's give a different color to the neutrons. So there's protons and neutrons at the center of this atom. Let's now go to one of the neutrons. So let me move this. Maybe we'll move it this way. Okay. So the next step is to look at a neutron. So again, this is uncontested science that a neutron is composed of three quarks and something known as gluons. Let me see if I have more colors. They all look the same. And three gluons connecting these quarks. And the glue and sorry, three
Glue,
quarks and three yes.
gluons.
What?
Gluons.
Yeah,
I
gluons.
just never heard. Yeah, haven't heard that before.
Yeah, gluons from the word glue. The gluons, but this is
Uh-huh.
from Yuri Gilmond, not from too long ago. Maybe I think from the 70s he came up with this notion that both protons and neutrons look like this, just a little bit different combinations of quarks, up quarks and down quarks. Not important. All we need is a neutron, and that's good enough. All right, let's begin now to increase the pressure, for some reason, I'm not going to explain now, but for some reason, the pressure of the star is going to increase. Let's say in our thought experiment, we can even say that we're pouring more and more and more mass on the star. It's possible in nature it actually happens that sometimes there's two stars, one of them becomes heavier than the other and starts drinking matter, sucking stuff from the other star. So one star can grow while the other one is shrinking. It can happen. So let's say our.
Can you
Go ahead.
sorry to interrupt, touch on why stars even start to what was it? Like to grow or become more like they have more pressure.
There could be.
Why do they develop pressure?
So I'm giving a theoretical reason. It's not critical because this is not how. It's not exactly how it happens in nature. I'm not going to go into in nature. If you wanna see YouTube videos that cover this, this is consensus science. So everyone agrees it's something called a supernova. Black holes form through a process known as a supernova. The what everybody says is incorrect, but it's good enough for you to see that I'm it I don't want to get right now into the detail of why everybody's wrong about supernovas and why I'm correct. I'm not going to go there now
Okay.
because what I solve now is something much more fundamental. As I was making lunch, I solved actually two very fundamental problems. One with general relativity, but it's not important. It's the same. I don't remember, but this is one of my most interesting revelations. So let's assume that there is a star, and this star has a neighbor, and it's sucking material because it has gravity. This one is heavier, the other one is lighter. So, or this one is denser, the other one is less dense. For whatever reason, there is a second there is a second star. We can draw it here. There's a second star, but I don't want to use this color because this is the color we said for the neutron. Let's go back to the black. So let's say there is a second star here, and slowly the first star is chewing, is sucking away the second star. This is the second star, and this is the first star, and we're discussing the first star. The first star is going to become a black hole. We're going to convert the first star into a black hole. 1 second, I have a message. Let me see that it's not urgent. Hold on. What happened? Not urgent, but interesting. Oh my God. A childhood friend is on TV. Very nice. Okay.
Okay.
Yeah, that happens too. So, okay. So are you okay this far? Do you have any questions? Anything unclear?
Yeah, are you saying that the first star, like the one with the one around it, it's gonna absorb the second star?
Yes, slowly. It's slowly absorbing, so it's slowly growing. And since the pool that we can imagine this that a star is a pool of water, so the pool of water is becoming deeper and deeper. So the pressure at the center is growing and growing. So far, so good?
Yeah.
Good. So this atom that we can imagine at the center that experiences the maximum pressure, here it is. It's composed of protons and neutrons. The neutrons are the greenish ones with the electron shell. We'll take one of these neutrons, and a neutron is composed of a quark, and a gluon. And this is standard science. Everybody agrees. No one some people disagree. I don't care. Most people agree. that by far most people. So this is standard science. Good. So let's now imagine that this neutron is under pressure. So this
Mhm.
neutron is, let's use the green color. Let's undo. So this neutron is under pressure. It's at the bottom of the pool, so it's under pressure. Now it's not, as you can see in the previous diagram, it's not really under pressure because there's all this space here. So where is the pressure? So the truth is that this star, because of the pressure, all the electrons are going to leave because it's too much pressure for the electrons. It's not going to be able to uphold this vacuum here. So it's going to drop the electron. The electrons are going to leave sooner or later, and the protons are going to lose stuff, and they're going to convert. They're going to decay into neutrons, and sooner or later, this star will become a neutron star, meaning a star of pure neutronium, only neutrons. And this is standard science. I didn't say anything weird. So maybe we can draw an intermediate diagram that the star became a neutron star. So we draw, so the star, so this the star is all green. So it became, everything is green. It's all neutrons, nothing but neutrons, because it lost this volume. So it became denser. It's much denser because in an atom, the nucleus, where the protons and the neutrons are, is tiny compared to the volume of the electron shell or the electron cloud. So this shell is huge. It's like a fly at the center of a stadium.
Oh
So
wow.
what?
Yeah, wow. That's like it shows how small the electrons actually are. Because electrons are very small,
Yeah,
so if containing it is much bigger,
it's not
that
only
means
that
the
the
electrons are actually more.
but it's not only that the electrons are small. It's that the electron cloud is huge, and the electrons, they end up leaving. In the beginning, they were, we had something called electron pressure, that any two atoms were pushing against each other because of the electron shell. But as the pressure grew, the atoms couldn't keep up. The electric force was not strong enough, and the electrons ended up leaving, and the two nuclei got together, and then all the protons converted to neutrons, and we end up with a neutron star. So, so a neutron star would be green. This is a neutron star. It's full of neutrons. So the star
Mhm.
became a neutron star. It's fine. It's good. So this is the neutron. So at the center, sorry. So at the center of the neutron star, there is a single neutron that again is experiencing maximum pressure. And this is the neutron at the center experiencing maximum pressure. So do you want me to review everything up until now?
Yeah, briefly go over it. I think I understand
Okay, okay,
briefly.
okay. So we had a star
Hmm.
that had atoms, which is protons and neutrons surrounded by an electron cloud. And we could view it like a swimming pool. So at the surface, the pressure is zero. And as you dive deeper and deeper and deeper and deeper, you get to the center. That's the maximum pressure. So there is an atom at the center of the sun or any star that is experiencing maximum pressure. Now let's imagine a sister star, and the first star is slowly drinking away the the gases. Stars are mostly gas. So it's drinking the gas, or it's inhaling the gas. So number one, star one, is inhaling the gas from star two. Star one is shrinking, star two is shrinking, and star one is growing. So the pressure on star 1 is growing. As the pressure on star 1 is growing, so in the beginning, you have electric pressure holding up the entire star, just like our planet. What's holding up our planet is electric. The electric pressure, the electron cloud bounces up against the electron cloud of a neighboring atom. So these two atoms are held apart by the electric, right? Because this is negative, because the electron is negative, and the electron here is negative. So negative and negative happen to repel each other.
Mhm.
Okay, so but because of the pressure at one point becomes so great that the electric force is not strong enough to push apart these two atoms, and they end up converging, and the electrons are too light, just like a balloon. If you push a balloon into water, it can't stay there. It pops out because it's so light. So an electron is like a balloon, and under pressure, it just abandons the star. So there's no more electrons in the star. And later on, all the protons and neutrons, some process goes on inside every proton, and it loses something and it decays into a neutron. Standard science. I don't remember exactly what happens. It's not critical. And all the protons become neutrons, and it becomes a neutron star. Here is the neutron star. It's much smaller than a normal star, because all this void in every atom between the electron shell is huge compared to the nucleus, the atomic nucleus. So we lose this huge volume, which is like a fly compared to a stadium. So we lose the stadium and we end up just with flies. So a neutron star is much, much denser. And again, we can view the neutron star like a swimming pool, and the surface pressure of the neutron star is zero. But as we go deeper and deeper into the neutron star, the pressure rises until we get to the centermost neutron that we can imagine, which experiences maximum pressure. Some pressure, it's the maximum pressure. And here is that neutron. Every neutron is composed of two quarks, three quarks, and I think three gluons. Uh, this was the color that we used for gluon. Gluon from the word glue, and quark. Gilmond said it's from some play. Three quarks for Mr. Something. It's whatever. Anyway, so that's it. So far, so good?
Yeah.
All right. Now, from now on, we're only going to talk about this neutron. We're going to convert this neutron into a black hole. And we can also take a neutron in laboratory conditions and convert a neutron in laboratory conditions into a black hole. So we don't need this entire story, but I didn't expect to go so deep into all the complexities. But we could have just begun with a neutron. We might as well have begun with just a neutron, and we're going to convert a neutron into a black hole from first principles using a pure thought experiment and simple science. All right, so let's take this neutron. It's at the center of the star. It's experiencing maximum pressure, and let's start increasing this pressure. Let's imagine the neutron star keeps absorbing more and more stuff from the sister star, because we said right now number one is a neutron star, but number two is still there. So number one still as so the neutron star still eats away at number two. It's still inhaling the gases from number two. Or alternatively, we can have a neutron in the lab and we can just apply pressure somehow to it. I'm not going to get into how to do it. I wouldn't know how to begin doing that. I don't know if it's possible. But let's imagine that we're increasing the pressure on this neutron at the center of the star. So far, so good?
Yeah.
Excellent. All right. So, as we increase the pressure, right, so a neutron doesn't really have this green layer. This is something that we can imagine. A neutron is just three quarks and three gluons bouncing around. That's all it is.
Okay.
So the gluons are like, you can imagine they're like springs. So as a quark moves away from its brother sister gluon, the spring pulls them back together, and as they move in closer together, the spring pushes them apart. And these three, they bounce around. They just bounce around, and that is a neutron. They don't bounce around inside because this layer doesn't exist. There is no membrane. It's just these three. So, but that's not important. Anyway, we're applying pressure to this thing, to this neutron somehow. We're applying pressure.
Mm.
All right, so let's take any two quarks. Let's put here, let's have a quark here and a quark here. Is this the color? Yeah, that's the color. And the gluon. The gluon is a spring. So we said if we pull two quarks apart, the spring is going to pull them together. And if we push them together, the spring will push them apart. All right.
Okay.
So now we're going to push these two quarks together. So so we're going to cause the spring to condense, to compress. All right.
Like magnets, right?
I
Like
wouldn't say,
negative.
no, you don't have to say that. It's just like two objects connected with a spring. That's all. It's just two objects connected with a spring. You don't even need to think about magnets. This is first principles. So you just need to think about two objects connected with a spring, that you can compress the spring or you can pull apart the spring. If you pull apart the spring, it wants to compress, and if you compress the spring, it wants to stretch. Right? You agree?
Yeah.
Yeah, it's very straightforward. But what happened? So what happened? Let's imagine, we can imagine a volume that contains these two quarks in the gluon. So what happened, you can tell, is that the volume, let me maybe take these guys away. Let me move this apart. So you can see that this volume became smaller, right?
Yeah.
Good. And this is already beginning to give you the hint of a black hole. A black hole, you said, is infinite density. Well, it's not infinite density. You don't need infinite density. Infinite density doesn't exist. We cannot imagine it, so we're going to ignore it. But a black hole has very, very, very high density. The density is so high that it causes certain phenomenon that we in general relativity, but we're going to ignore that for now. We'll come back to what a black hole does exactly. Anyway, so we compressed the volume of these two quarks and the gluon. But if we go back to our neutron, if we imagine the neutron, we can do the same with the three quarks, of course. We can imagine three quarks and compressing. So we have, let's say, the original three, whatever. So we had this. This was in the beginning. And now we compress the neutron and we have a smaller volume. So the neutron is now in a smaller volume with the same mass. So,
Oh, wow.
What?
Yeah. I said wow. Like.
So the same mass, right? So density, the equation for density, we use the Latin letter rho. So density is mass divided by volume. So if we have the same mass as before and a smaller volume, so the volume went down. So because of simple mathematics, it must be, in order for this equation to still hold, it must be that the density went up. It's really that simple. So the density, the effective density has gone up. Do you agree with this?
One sec, so yeah, this seems true. Yeah. Okay.
It's just a definition. I mean, nothing changed in the universe. It's just a definition. Since you brought up density, I don't think I would have brought up density, but you brought it up, so I'll go with it.
Mhm.
But something strange also happened to the mass because because as we compressed the two quarks and the gluon, we actually did something called work. Because when we compress, right? So let's imagine I'm a tiny person and I used my left hand. I held my left hand here and my right hand here, and I pushed my right hand towards the center and my left hand towards the center, and I compressed the two quarks towards each other. So I did work. Work is actually defined as force. I applied a force.
Divided by
It's
density.
it's actually times distance. So I
Oh, okay.
applied if you
That's what I
apply,
remember myself.
yeah, it's it. But again, this is I promised first principles. It's first principles. So as we apply force over distance, here is the distance d. Applying force over distance, so force times distance actually is defined as work. It's just a definition, just like uh, mass over volume is defined as. It's a definition. It's just a definition. It's not even an equality. So, but this is what we call work. This is work. And guess what? Work is also defined as energy. Work is energy. I'm pretty sure work is energy. Let's check. Let's go to Google 1 second. Is work equal to energy? I also forgot my basic physics already. I don't do.
Okay. I remember this work done thing in physics. You work
It
done.
says here. Let me maybe find a Wikipedia. Is there a Wikipedia on work and energy? I don't see Wikipedia. There it is. Work. Let me get work. Is it a good link? Looks like a good link. Copy link. I'll put the link. I want to put the link here. There it is on the side chat. Link. All right. So in science, work is the energy transferred to or from an object via the application of force along a displacement. Yeah, force times displacement. In its simplest form, let me look at an equation. Maybe let me go to this thing. Let me open it up on my side. Yeah. Work is force times distance. Can I copy this? Let me try and copy this. It's going to be, oh, it's an image. Okay. I'll copy the image. Will it let me? It's black on black, but it says here that work is the integral of a force vector times a tiny distance, but it's the integral over the distance. Anyway, it's force times distance. Yeah. Work is force times distance, it's fine. So No, work is force time. No, but is work energy? So they said work, but is work? I want to just see an equation. Is work equal to energy? Oh, they say work is the delta energy. Let me see. From Newton's second law, it can be shown that work on a free, no fields, rigid, no internal body is equal to the change in kinetic energy corresponding to the linear velocity. I think it's. I think I'm. Work is energy. I'm just looking for someone who says it explicitly. Let me look up work equals energy. Is this true? According to the work and energy are intimately linked. The concept of work is defined as the energy transfer to or from an object. Okay, so we're transferring energy. So we can say that we're transferring energy into this system. And
Mm.
guess what Einstein said about energy? So here again, I'm using first principles. We're going to use, guess what? Energy equals, you tell me. What did Einstein say energy equals?
Mass divided by something.
Yeah, everybody knows it. E equals M,
Divided by D. I don't know. MC.
almost. Einstein said E equals MC squared.
I don't know, man. I
Nah,
told
it's
you
fine.
I'm
You
like so
never.
bad at
It's
science.
fine. It's fine. You never heard E equals MC squared?
No,
Yeah,
I have.
yeah. I promised you basic science. This is 100-year-old science. I've never derived E equals MC squared myself, but the intuition is that energy and mass are interchangeable. There, there is a thought experiment we can do to convert to show that the energy and mass are interchangeable, but we're not going to do it now. Maybe a different time
Yeah,
we'll
I
do
am
it.
interested in that though. But yeah,
Yeah, yeah,
go
yeah.
ahead.
Me too. Me too. Yeah, we'll come back. We'll come back to make sure everything is correct, even though Einstein said so and everybody agrees. Look, it's also about the quark, about the neutron. I mean, we're assuming this is correct. I mean, Gilman came up with this model, but no one is. I don't think anyone has ever seen a quark. I don't think you can see a quark because they always are attached to a gluon in another quark. So you can never. I don't think you can see a single quark. That's why there's people who deny the neutron model, the quark model. They say it's
Mm,
nonsense and it's unscientific.
interesting.
For sure. So what do we have? So guess what? So we introduced force times distance. We did work. We introduced energy into the system, meaning the energy. Let me ask you, which system has a greater energy? The relaxed spring on top or the compressed spring at the bottom? Which system?
Com compressed.
Yes, because we introduced energy. We pushed in. So we did work. So
Is
this.
that like
Mhm.
potential energy? Like
Exactly.
if it like,
As
yeah.
long as this, as long
Okay,
as
yeah.
this,
Because like
exactly.
just let me get my own. Let me feel good. So you're gonna have potential energy. So that's like the energy which an object can have.
Well,
So when you compress the spring, you have the potential to expand
exactly,
rapidly, and that's potential energy. Okay.
exactly,
Right.
exactly. So the energy that we introduced into, I think the two quarks they have a name. Two quarks are called something. They renamed it as a different object. The standard model of the quarks combined composite particle two meson. Two quarks can form a meson. Let me give you the link. Quark. Let me just. I'll give you also a link so you know that this is standard science. I didn't make anything up. This is not some obscure science. This is absolutely standard wiki stuff. Here is the neutron. A quark is a type of elementary particle and a fundamental constituent of matter. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons. Anyway, this is standard. I didn't introduce anything new, so don't blame me. I'm just a messenger. Anyway, so the energy, I agree with you that the energy, right? The energy of this guy is lower and the energy of this guy is higher. So the energy went up. All right. So if the energy, let's go to E equals mc squared. So E is equal to mc squared. Let's assume we want to maintain the equality. So if E goes up and c must be a constant, according to Einstein, the speed of light is a constant. We assume that's one of the assumptions. The speed of light is a constant to all inertial observers. We are an inertial observer, so the speed of light must be a constant. So the speed of light cannot change. So if energy goes up, what must happen to the mass of the meson or the neutron?
So when you say it can't change,
It's a
I don't know.
constant. It's 800. It's always 300,000 meters per second. It's always 3 times 10 to the 8.
Okay.
Is it 8? 6 is million. That's too much. I don't know, some number. It's some number. I don't remember the number. Can I do Control Z? It's 3 times 10 to some number meters per second. It never changes. We always observe it to be the same. This is tested. We've tested the speed of light. It's always a constant. It's a constant of nature. It's one of the constants of nature.
Is that like depend? I know some people, they say like it's faster underwater or slower or something.
Yeah, it's slower. It's faster in a vacuum than it is in a non-vacuum. The speed of light in a vacuum is a constant. The speed of light in any material is a constant, but these two constants are not the same. But we're assuming that this is a vacuum, or it doesn't matter. It's the conditions haven't changed. So we introduced more energy. Let's assume the speed of light is a constant. We're just going to assume the speed of light is a constant. This is like, it's normal to assume the speed of light is a constant. So you can go along with this assumption. We can later come back and assume maybe it's not, or why do we assume that it's true? And I might be wrong, but most people that you would talk to and you tell them I'm assuming the speed of light is a constant, they wouldn't bat an eye. They would say, fine, of course, the speed of light is a constant for all inertial observers. Inertial means not being pushed, not accelerating. So far so good?
Yeah, very good, yeah.
Okay, so the question is, we said we're increasing the energy of the meson or the neutron. We're holding the speed of light constant, and we're holding the equation true. So what must change in order for all these conditions to be true? What must change?
I'm not too sure.
It's just a mathematical equality. So if it was equal before, if you can imagine equality, so the idea of equality is really, you can imagine this as a seesaw, as a balance. It's a seesaw. So there is a seesaw, and here is the fulcrum. You call this a fulcrum, and whatever is on this side balances with this side. This is what the equality sign says. So if you increase this side, you must increase. If you don't increase the right, it's gonna right. The left will go up and the right will go down. So in order for
okay. So are you saying that for the formula to change, you have to change one of the variables or something?
But first, tell me about the seesaw. What must be true if we increase the mass of the left?
Yeah.
What must we do to the right in order for
Oh, the
the
right's gonna go up if that's lighter.
no? But if we want the balance to be maintained, we want.
Oh, you have to equalize the mass on either side
So what should I do to the right side?
and make it the same weight or mass.
Yeah. Yeah, you have to make it the same, whatever, right? So the right side of the equation must, if the left side of the equation goes up, increases, then in order for the equality to be maintained, we have to increase the right side by as much. But since we're holding c, the speed of light, as a constant, what must we do?
Change mass.
Very good. Change it up or down?
Up.
Very good. Why?
Well, because the energy is going up.
Very good. So the left side of the equation went up, so the right side must go up. Since the speed of light is a constant, we cannot modify it. The only thing we can play with is mass. So in order for Einstein's E equals mc squared to be true, to remain true, if we introduced energy into a system, it means that its mass must have gone up. Meaning, if this was the original mass of the system, the new mass must be greater. Must be greater. So not only did the volume go, what happened to the volume? Remind me.
Well, you condense the volume, so
Very
the one.
good.
Yeah.
Very good. So the volume went down, and the mass did what?
Went up.
Are you sure?
Well, oh, it stayed the same. It stayed the same.
The mass stayed the same?
I believe so.
But
Yeah.
what did we introduce? What happened to the energy?
It went up.
And what did Einstein say about energy and mass?
Oh, they are interchangeable.
Very good. So if the energy went up,
oh, the mass would go up as well.
If Einstein is correct,
The-
assuming Einstein is correct, we'll come back to Einstein equals mc squared to figure out if it's nonsense or if it's true. Assuming Einstein is correct, equals mc squared, then the mass must have gone up. Do you agree?
Yeah.
Okay.
Yeah.
It's an assumption. We'll come back to this assumption. We'll take care of it later. For now, we said we're starting from first principles, equals mc squared. For now, it's a principle that we're starting from. It's a first principle. It's good enough. All right. So the mass went up and the volume went down. All right, let's go back to our density. So the volume went down, and what happened to the mass?
Up.
It went up. So what happened to the density?
Say this. I guess down, but it's interesting.
Okay.
I guess down.
Wait, it's the
Yeah,
same.
that part's confusing.
It's confusing. It's the seesaw. So whatever is
Okay.
here is the same as here.
Uh-huh.
So if this goes up, then the right side must
Go up. Yeah.
go up.
Go up.
So both sides went up. So
Yo, guys.
hey, what's up?
Hello.
Hello. Oh,
Okay.
there's many people with us.
I'm afraid to leave the whiteboard because I might log out on the set.
You can leave.
Oh, British.
You can
Are
leave.
you British, mate? Are you British? Yeah. You British? Yeah.
I am British. Yes.
Yeah, me
Like,
too, mate. I'm British. Yeah.
David Hume as well. Yeah.
Yeah, mate. That's my uncle. Yeah. I can't read this. It's gibberish to me.
Well, you came late. You came late to class.
Yeah.
So
Exactly.
there's a video. It's recorded on YouTube, and the link The link is somewhere. Let me see where the link is. Let me give you the link to the video. 1 second. We're developing a black hole from first principles.
Oh, I get it.
Yeah, it's very straightforward.
Wait, so I'd probably here. Can I do something over here? So
Hmm.
probably do like P. Okay, I gotta zoom in some more. So P and then like phi such that
Okay, so you have like
wait,
E equals mc squared Einstein, relating energy to mass, QED equals H, quantum electron.
Wait, what are
Is
you guys?
somebody drawing?
I don't know.
I don't know
Yeah,
what's
but
going
I don't
on.
know. What are you guys doing? I don't know what you're doing.
I'm just looking at Newton's second law because you just you said.
No, no. We're look. I. If you want to listen to what I'm saying, guys, we're recording this on YouTube. I don't want to waste time. I don't know what you're doing. Do you want to explain what you're doing and why?
I'm just
No,
reading it what it says.
you just carry on because they came late. So
All right, guys. Just don't write in my region of the blackboard, please.
okay. Yeah,
Okay,
that's
Daddy.
fine.
All right. So, oops. So, what's going on? Oh, I'm not in the blackboard. 1 second. Okay. So, all right. So just stay away, stay away, stay away. Don't write in my little blackboard. All right. So this time we're going to say we mass went up. I'm sorry. Let me undo the last thing I did. So we're saying mass went up on the right side. So on top of the fact that before we talked about the volume going down, now we're saying mass went up. So if mass goes up, assuming the equality was true before, so everything was balanced, and I increased the right side. What must I do to the left side for the equality to hold?
you have to do the same.
Well, you have to
So you
increase.
have to,
You have to
yeah,
increase the left
yeah,
side.
exactly.
Yeah, yeah. You have to increase the left side. Meaning, as we increase the mass, the density grows even more. So when volume goes down, if the same mass, the volume goes down, the density goes up. And if the same volume, the mass goes up, the density goes up. If both the mass goes up and the volume goes down, well, the density goes up even more. It's fine, but it's fine. All I'm saying is that whatever is happening is just making the density greater and greater. So the density is higher and higher. So as we are increasing the pressure on our neutron, the density of the neutron is growing. That's all I wanted to say. The density of the neutron is growing. Its mass is going up and its volume is going down. Now you could say, how could you say that the mass goes up? We know, what does it mean for a mass to go up? But that is what Einstein, according to Einstein, that's the result. The mass of the neutron must go up, and the volume, because of the pressure, must go down. So as the pressure increases, the mass of the neutron goes up, the volume goes down, its density goes where?
Repeat that. So as the mass goes up,
As
the
the
density is also go
well,
up as well.
well, we're putting pressure on the neutron. So it's what happens to it? You tell me. What happens to it? What's the story?
So as the mass goes up,
Wait,
you have to.
before. I mean, first we're putting pressure. What happens when we apply pressure?
Uh, I don't. What do you mean when you apply pressure? Oh, so it's more denser. So
Yes.
what's it called? The it's gonna become more compact.
Very
What
good.
does the V mean? What does the V mean again?
V's volume.
The volume is smaller, but it's gonna have the same density.
Well, if the volume is smaller, the definition of density is mass over volume. So
Okay, volume goes down.
if the volume goes down, what happens to the density?
The density would go up.
Yes, by definition. That's the definition. Three equal signs is a definition. The definition of density, just a definition, just a word in English. The definition is defined as mass per volume. It's just a definition. So if the volume goes down, so
Mass goes up.
assuming the mass remains the same. If the mass remains right in the beginning, we're applying pressure on this neutron. So it begins to compress. Every two quarks, every meson, the two quarks are called a meson. This is called a meson, just a name, nothing more. This is this okay. So as we're applying pressure, the two quarks are compressing, the volume shrinks. As the volume shrinks, let's assume the mass stays the same. What happens to the density?
Yeah, I don't think you've covered that, but I would assume it would probably you're gonna have to be the same on either side. So maybe this is gonna go down as well.
I mean, so the thing with when you divide, if you divide, you can think of dividing by a very big number. If you divide by infinity, what happens? What happens to the right side? Let's say the volume is infinitely big.
Uh-huh.
So as V goes to a bigger and bigger number, what happens to this number? What happens to 1 over V? As V goes up, what happens to 1 over V?
Oh my god, I don't know.
I mean,
I don't know.
this is like
Infinity is so confusing.
yeah, I know. As the volume goes to infinity, what happens to 1 over V?
It's the same, I guess. I don't know. It's infinity divided by 1.
If
It's still
if you
infinity.
if you take an apple and you divide it by 2, so what do you get? You just take
2 apples.
no, but let's say
Yeah,
you take,
just one apple cut in half. What?
yeah. If you take half of an apple, then what do you have?
Half of an apple.
Exactly. And if you cut that in 2 and take one piece, what do you have?
Well, you have 2 pieces.
No, but you take only one. You cut 2, you take only one of them.
If you take one, you have 1 piece.
But what is the size of that piece?
Smaller.
But what is it? It has a name. So in the beginning,
Quarters.
it's what?
Quarters, I guess.
It's called a quarter.
Yeah, I said that quarters. Yeah.
Oh, you said a quarter? I thought you were saying forter.
No, quarter.
No, but you can also
Yes.
say forter. Forter is the same, like four. It's a fourth of an apple.
Oh.
If you cut a
Okay.
fourth of an apple in 2 and you take one piece, what do you have?
You have 1/8 now.
Exactly. So so if you cut an apple into many, many, many pieces and you take one of them, then what do you have? A small piece or a big piece?
Smaller.
Smaller and smaller and smaller. So as we're dividing the whatever we have by more and more and more and more, and we take only one of those, one of many is big or small?
Oh my god, I want to get it smaller.
Yeah. And if it's infinite, as it tends to infinity, as you tend to take one out of infinity pieces, what are you approaching?
0.
Exactly. You're approaching 0. Anyway, but
This
this is like basic math. I understand you haven't done math in a long time, so you have to brush up on math. I haven't done math in a long time. I also had to remind myself all this stuff. Anyway,
I'm like taking mathematics back up though, but yeah.
you taking mathematics?
Yeah, back up. Like I have a new interest in mathematics, so I'm starting again.
Very good.
Like, you know, yeah.
Mm-hmm.
Yeah,
Yeah.
go ahead. I'll put
Excellent.
that in.
So, anyway, look, we have a neutron. We're applying a force or a pressure from all direction on the neutron. We're causing it to compress. The volume goes down. But as we're compressing it and the volume goes down, we have done work. We're compressing the springs. There's now energy loaded onto the springs, onto the gluons. The gluons have now potential energy. There is potential energy in the neutron. The smaller neutron is more potent. And according to Einstein, this means that the neutron has become heavier. Its mass is greater because E equals mc squared. There is a direct relationship between energy and mass. So you put energy into a system, it's a heavier system. It weighs more. Its mass has increased just because of E equals mc squared. That's the nature of the beast. For now, we're assuming E equals mc squared. So far, so good?
Yep. So far, so good, yeah.
Okay, let's continue. So let's now... So let's talk about the next step is... I don't know if I should go all the way to Newtonian gravitational field. Okay, I got it. All right, let's go to the equivalence principle. Have we discussed the equivalence principle?
I don't think so.
Okay.
What is peaceful? I'm not too sure.
Okay, so we probably didn't.
Yeah.
Okay. So again, so the next chapter, this was one chapter. We'll come back to it. We have an increase in rho, an increase in density. That was the conclusion. The conclusion is density went up. We can call this equation 1. We can save it, and later on I'll reference equation 1. That's what it means. The density of the neutron went up. All right. The next step. Can I clear the blackboard from their nonsense?
What did they write?
Yes.
Oh wow.
I think this guy
wait.
I think this
This
guy.
is like predicate logic for some reason.
Oh, I don't know what it is, but I think this guy actually knows math or knows something.
It's just logic.
Okay. So this was one chapter. The second chapter is we're going to start again from first principles. Maybe we'll start. Let me see. Okay, we'll start here at the top. Let me magnify. So difficult to use the control every time you want to drag it, and then I wouldn't know how big. No, what I'll do is I'll take everything we did thus far, and I'll just move the whole thing to here. This is chapter 1. So, is there a square? Can I draw a square?
Are you drawing? If you're drawing, I can't see anything.
Wait, you're not seeing what my blackboard?
I can see all you have written, all the blue ink. green, red, black. I can't. Oh yeah, I see the square now. Yeah.
Yeah, I'm trying to make an empty square, so I guess it's impossible to make an empty square. All right. So let's undo. I was gonna draw like something around it, but oh, maybe a line. Forget it. I'll just draw like before with a pencil and some color. This is chapter 1. We're done. Okay, chapter 2. Chapter 2 will start from first principles again. Let's get rid of this. Okay, now we're going to talk about something completely different. The following experiment, the following thought experiment. So, you are in a spaceship. Here you are in a spaceship. And the engines, there's engines here, but the engines are not running yet. And here you have a hose with water. And you're going to fire tiny molecules of water at almost the speed of light. Well, first you're going to fire them at normal rate. So water comes out. So do you think it's going to come out in a straight line or a curved line? If there is a hose here and water coming out.
It should be straight.
Yes,
right?
yes, you're in outer space. The universe is empty. There's only you inside a spaceship. The engine is off. You have water and a hose, and water is coming out. So, is it a straight line or some other line?
I mean, can't just say straight, but I know with gravity and all of that
No.
stuff in
So there is no
Okay.
gravity. That's the point. You're all
No.
alone in an empty universe. This is an empty universe. It's a thought experiment where you're all alone in an empty universe.
I guess it's gonna be the light's gonna be affected by the lack of gravity. Then
Light? No, this is water.
you said it's coming out at light speed.
No, let's assume it's not. Let's make it a normal speed. It's just water coming out at some normal rate. Just
Oh, okay. It's not gonna go straight. It's gonna like bendy and stuff
bend to where?
down.
Why
I
down?
don't know.
There's nothing
Yeah, down.
around. The universe is empty. There's only you inside a spaceship with the engine off. There's nothing else.
Is it? I don't know. Look, is it gonna go everywhere? Like what?
Well, but it's the hose is directing the water. So the water comes out, there's like a jet. It's a jet of water coming out kind of fast. Like it's a garden hose. So the water is coming out. Where would the water go?
Up, down, left, right, everywhere.
Why? The
Because
hose,
there's no gravity.
but the hose is directing the motion of the particles of water. So because of inertia, if you look at each particle of water, because of inertia, as long as it was moving in a certain direction at a certain speed, as long as it's not impeded, as long as it's not interfered by anything, it's not interacting with anything, why should it change its direction? So every molecule of water, as it leaves the hose, it's going in that direction. Why should it change direction or speed? So
I guess I just thought like in space, like because there's no gravity, you can't remain like grounded on Earth, so things are gonna go up and everywhere like that.
but let's
But
assume
if it's shooting at light speed, I guess that couldn't override
No. It's a normal
Overall,
speed. It's a normal speed.
Yeah.
You're firing.
I don't get it. I don't get how it's not gonna go everywhere then or up.
Well, let's look at each molecule of water as it comes out of the water hose. As inside the water hose, you agree. Let's magnify the water hose. So the water hose is basically a pipe. So, and here's a molecule. Here are molecules of water. So as they are in the hose is forcing them all to go along the hose in one direction. Do you agree?
Yeah.
Good. So as they come out, why should they change direction all of a sudden? Why should this guy suddenly go this way? And why should this guy suddenly go that? Why should it? What's gonna what's
I guess I was thinking like the further away from the outburst of the hose, he's gonna lose the speed.
why?
He's not gonna.
But there is no air. There's nothing. The water molecule is not interacting with anything. So why should it change its direction, its trajectory?
It doesn't have anything to keep it going
Why?
on the same trajectory.
Okay, so Sir Isaac Newton, he came up with 3 laws of motion. So the first one was the law of inertia. So he said an object will tend to keep going in the same speed and direction unless it's interfered with. Unless there is a force applied to it, it's going to keep going in the same speed and direction. That's one of.
I see.
And again, that's first principles. Everyone agrees. This entire civilization today is built on Newton's laws of motion. So inertia.
Yeah.
Okay, inertia is like it's from first principles, because if you throw an object, it's going to be influenced by gravity. But if you ignore gravity, then you think about it, an object, like if you take a ball and you kick it, it's going to go in the same direction in speed. It's just going to slow down because of friction and stuff. But if you ignore friction, if you had a frictionless world, then the ball would keep going forever. It would roll on and on and on forever. What did I say? A ball, yeah,
Yeah.
So it's just inertia. Everyone agrees that the law of inertia is correct. This is first principles. We can look up wiki, the law of inertia. The law of inertia. So where's wiki inertia? There it is. Copy and paste. There you go. So Newton's laws of motion. Newton's laws of motion are 3 physical laws that describe the relationship between the motion of an object and the forces acting on it. These laws. Okay, but where's the? There it is. A body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by an external force, whatever.
Yeah.
All right. So what's going to happen then to these 2 water molecules, do you think?
Yeah, they'll stay the same. They're not gonna go up or down.
Very good. So they're not going to go like that. Indeed.
That's very interesting though. Like I'm learning a lot. Yeah, it's very good.
Yeah. They're going to keep going. So what should happen to this water jet? What should it do?
The water jet?
Yeah.
What do you mean? What's going to happen to it?
Will it go in a straight line or curve or change direction? What's going to happen to it?
It's just going to stay the same
Good,
inertia.
good. For how long? 1 meter, 1 kilometer, 1 billion meters, 1 trillion meters. For how long will it keep going?
Until something impedes on it.
Good. And let's say the universe is empty. So there's only you, the spaceship, the engine, the water, and the hose.
Well, only those things can interfere. So as long as we don't do anything, it's gonna do the same thing forever.
Exactly. Exactly. Good. Very good. All right. So now, very good. The next step we're going to do is we're going to turn on the engines. So let's turn on the engines. And what's going to happen to the spaceship?
So repeat. Somebody entered my room. Sorry.
Yeah, it's okay. So we turned on the engines.
Yeah.
We started the engines. So the engines are now pushing. The engines are going down. I mean, the gas expelled is flying down very fast. What's going to happen to the ship? What do you think is going to happen to the ship?
If it's all going down, is it all going down?
The gases expelled
Mhm.
by the engine are flying down at a very high speed. What do you think will happen to the spaceship?
Goes down as well, along with the engine.
Well, so this now we come to Newton's, I think, second law of motion. It's called for every action there is an equal and opposite.
Oh yeah.
So what do you think will
So
happen?
if that goes down, when the spaceship's gonna go up.
Very good. So this
Yeah, I knew. Yeah,
very good.
but I just need sometimes I need you to jog my memory. I know
Yeah,
about that law, though.
that's good. That's good. So the exhaust is flying out very fast downwards. That means the spaceship is compelled to move upwards. Very good. Now you are looking all this time. You're looking at this jet. What? So this jet has been going out for a while, but now that you're beginning to go up, what do you expect this jet to look like to you?
What do you mean?
When you look right before we started the engines, you looked out and you saw a straight line of water.
Uh-huh.
Now
Oh,
that the
okay.
ship is beginning to accelerate upwards, what do you expect to see?
Is the water also going to go up?
But okay, so let's do this. Let's use a different color. So let's say, right, the engine started, the spaceship is moving up. So here is the spaceship moved up just a little bit to here. So your head moved up just a little bit to here.
Okay.
And the water coming out, the pipe is now here.
Mhm.
And the new water coming out, here is a molecule, it's here. But the molecule that came out before, just before, is here. Right? The old molecules didn't change position. The old molecules that came out before the ship started accelerating, they're still here. They haven't changed. The new ones are coming out here. Now, in between, they were coming out somewhere in between. So as you keep going and going, what do you expect? So now let's say your head or the water hose, when the water hose is here, what do you expect to see? What do you expect the shape? Go ahead.
Well, presumably it's gonna go down.
But
I don't know.
Right.
Things don't go over my head.
Yeah, it's actually difficult to imagine. You just have to play with it in your mind. But right, you can see here that it's like it's curving downwards. Right, as you keep moving, right, this molecule is moving forward. It's gonna in the future it's going to be here, and this molecule is going to be here, and this molecule is going to be here. Um, but basically, right, the new molecules are here, and the old ones are somewhere else. And this is basically what it's going to look like. It's going to be curving down, and where the spaceship started accelerating, it's going to curve back, and it's going to be a straight line.
Wow, that's very weird, I guess.
Yeah, but this curvature, this is the beginning of general relativity curved geometry. This is where the curved geometry comes from. So
Oh, I really like geometry.
what?
Yeah, I like geometry. Like that's my favorite
Well,
mathematics.
curved geometry is Einstein's general relativity. So E equals mc squared, that comes out of special relativity for somehow. I don't know how. We need to go back to that. But in general relativity is about the curvature of the geometry. It's our geometry, the whatever. We'll come back. I mean, we're not going to come back. We're going to develop it right now. We're going to develop the curved geometry and the motion of space. How are you doing thus far?
Yeah, very good. Oh, I will say though,
Yeah,
I will have to leave in about 10 minutes. So I'm going out
it's fine.
like exercise.
It's good. You know what? We can stop here because I don't want to kill you with so much information. I want you to absorb it. In order to absorb it, you need to sleep on it. The way the brain works, incredibly enough, is that you need to sleep on information in order for it to be absorbed. Did you know that?
No,
Yeah.
sleep as in just you need to let it process. Right.
You need to let the brain process the new information. So the way
Oh, okay.
the brain is going to, when you sleep, the brain actually takes today's experiences and replays them again and again and again and again, and that actually becomes it reshapes the brain. It burns in new pathways, and that is your long-term memory.
Interesting.
Yeah.
I'm reading about that sort of stuff as well. I don't know if you know about Freud.
Yeah, I don't
No.
I don't know if I care so much about Freud.
Why not? I like Freud.
Yeah, but the question is what he had to say, is it scientific? Has it been validated scientifically?
Yeah. Okay. Yeah. Sure. But
So be careful, just be careful, because you can ruin your life if you go with the unscientific way is the path to darkness, literally. Forever will it consume your soul.
interesting.
Where is that from?
It sounds like something from the Matrix.
No, it's from Empire. That's Yoda.
What's that?
The Empire Strikes Back. You never saw it.
The unscientific way Yoda said that.
No, he said that about the dark side. Forever. He said something like that when he explained to Luke Skywalker what the dark side is. What is the dark side? Wait, you've never seen Empire Strikes Back?
No, I have, but I haven't watched. I don't. That's not one of my favorite films. I haven't watched that in forever.
No, Empire Strikes Back is one of my favorites. Star Wars and
Oh,
Empire
for real.
of the
What,
entire.
the dark, yeah, the dark side is a pathway to many things. I don't know. I'm trying to figure out what they were saying. I don't remember.
That's from episode 3. So I'm quoting from.
Yeah, Revenge of the Sith. Yeah.
Yeah, so in Revenge, so Darth Sidious, that's what he explained to Anakin about the dark side.
Would
Yeah,
consider
yeah,
unnatural. Yeah.
yeah. Sidious
What
was,
is
yeah. What?
interesting? Yeah, I haven't watched Empire Strikes Back in forever.
So in order to stay on the light side of the force, you really need to be very careful because it's very easy to fall into the dark side. And then it's very difficult to come out because it consumes you.
Yeah, I guess so. Yeah.
Like most people live in lies.
Mm.
Anyway, we'll come back to that. Anyway,
Yeah.
so I'm gonna let you go. We can continue some other time. Thank you so much. I'm gonna stay here. If you want, I'm gonna. I see I have 2 comments in my on YouTube, so I'm gonna talk to people. You can stay or leave whenever you want. I'll see you later, man.
Okay. Thank you, and take care.
You too. Thank you. Bye. All right.
Bye.
So bye bye. So we have a comment here from P Man. Yeah. So he disconnected. That's good. So P Man plays 44. Why was this in my? I don't know. I don't. I guess YouTube decided that you need to know how black holes are formed. That's YouTube's decision. I don't know. And engineer Masood says exactly. So YouTube is ending up recommending my channel to random people. That is so funny. That is so funny. But I appreciate YouTube. YouTube is really amazing. Anyway, okay. I think that's good enough. It's been an hour and a half. It's been very, I think, very intense for anyone who comes without a background. People with a background, they already know where I'm going, but they still don't understand it. But they can already begin. Anyone with a lot of experience, they can already see how I'm going to convert a neutron into a black hole. But we'll do it from first principles in a thought experiment, slowly, with no. We don't need any weird information. Nothing weird. We're gonna do just the very, very most basic stuff. We'll create a black hole and we'll see that it's nothing special. There's nothing special, certainly nothing weird about a black hole. It's not weird, it's not special. It's very mechanical, it's very straightforward. No, nothing to be confused about it. We should not become confused by any nonsense, in my honest opinion. All right, everyone. Thank you for now. We'll do chapter 2. Maybe we'll need a bunch of more chapters. We might need to go back to maybe take care of E equals MC squared. Maybe not. I don't know. It's not so critical for me right now. I just want to explain how we create a black hole in from first principles in a thought experiment. And once we understand a black hole, we'll see that there's nothing weird about it. There's nothing hidden. It's really straightforward. We shouldn't let anyone confuse us with what a black hole is. All right, everyone. Thank you very much. You've been very kind. See you next time. Bye bye.